Right. Hello, everyone. Welcome to the robotics seminar. We meet every Friday, have a lot of distinguished speakers. Um, Today, it's a real pleasure to invite Tapo. Our prodigal son has returned, like Abhishek mentioned before. Tapo did his PhD at Cornell with Charlie Kemp. Sorry, at Georgia Tech with Charlie Kemp. Did some really incredible work then on getting robots really close to people and touching them, and both in terms of like tactile sensing as well as the controllers around that. And then he came to UW to do a postdoc with me when we were just starting out on like taking the next steps on our robot-assisted feeding project, and really like along with Maya and a lot of the others, took the project to really the next level. I think that really exemplifies Tapo's skills. Not only is he an excellent roboticist, but he truly cares about the people that he is building these robots for. And you'll see that throughout the talk today, is that it's not just about the robots or the algorithms, but the people for whom you're building these robots and algorithms. And I think I have learned a lot about that empathy and the caring for the true customer, the true user. And very rarely do we have the opportunity to affect real people's lives in the work that we do. But I think this feeding project and all the other work that Tapo has done since gave us a really nice window into at least thinking about what it means to be somebody who can't move anything below their neck, and what it means to empower them so that they can feed by themselves and live a life of greater dignity. And I learned a lot through this working with Tapo, as well as all the other brilliant people that Tapo mentored. And after he went to Cornell, he's really taken this project to an even greater level. It's always fun for me to see others taking projects that we've built and taking it in directions and dimensions that we never thought that were achievable. So I'm really, really excited about that. I always joke with my postdocs that academia is cruel in that when I go to funding agencies now and I tell them hey, I can build this robot that can feed you, they're like, well, Tapo does it better. Why would we want to fund you? So maybe I need a cut of your earnings now. But it gives me no greater pleasure than to hear that from our funders, that people who we have hopefully imprinted some of our knowledge on have gone on to do amazing things. So, Tapo.
Thank you so much, Sid, for such a kind introduction. I used this for the students in the crowd. I don't know how you feel when you have to present in your lab meeting in front of our advisors. I am kind of feeling like this now. Am I living up to the standards that Sid and Maya? They have are they? It's okay. Let's see what Tapo has done. So I'm kind of anxious, but we'll see. Cool. All right. So as Sid mentioned, so my full name is Tapomayukh Bhattacharjee. Everybody just calls me Tapo, and I lead the EmPRISE Lab at Cornell University. And today I'll give a talk about some of our preliminary work in this. Of course, every work is done by the amazing students. I am just presenting, on their behalf. Cool. So the way I think about, caregiving. So what I'm going to do is, for the next few slides, I'm going to talk about why is physical robot caregiving or physical caregiving in general hard? What are the challenges? Then I'll start talking about some of the things that we have barely started doing in that direction. So first, physical caregiving is very multifaceted and contextual. Okay, it's because this is just one aspect. You can there are various tasks like ADLs. These are called activities of daily living: eating, bathing, toileting, getting dressed, getting around inside, getting in and out of bed, transferring, or also various instrumental ADLs that help people in their day-to-day life, right? So there are various tasks, but not just that. It's also about users, right? And every user is different in many different aspects. So for example, here, different in functioning abilities. On the left, Tyler, by the way, I got in touch with Tyler while I was at UW. Unfortunately, he's passed away, but I mean, the contributions that he has made in our work is just, I cannot overstate this. So Tyler, if you see here, his mother is feeding him, but he is moving his neck a little bit to be able to eat. But here William is feeding Henry, and Henry can only chew food from one side of their mouth. So the same task leads to very different caregiving strategies because the users have functioning abilities. So as roboticists, especially for these user-facing applications, you don't just think about variety of tasks, you have to also understand the user aspect, right? Every user is different. But now every user is not just different based on their functionality, they also have different behavioral traits. Tyler loves to eat while he's watching TV, like baseball or something, and Henry actually tries to provide his intent to eat, take a bite by looking at the caregiver. And again, tasks, users, it's also about environments. Here, Henry is being lifted out for the same task of, but here, because the environment had a Sarah lift versus here there's a wheelchair, you see a very different caregiving strategy. And finally, for the same task, different caregivers may use very different strategies. William just lifts the leg to dress pants, but Jane is folding, and then because of because Jane cannot just easily lift the leg, Henry is very tall, doing the same activity in a very different way. So my main point that I'm trying to show you through all these slides is that caregiving is very multifaceted and contextual. It is dependent on the tasks, it is dependent on what environment the user in, it is dependent on every user, and every user is different, as well as who is giving the assistance. Okay? So now, why robots? Do we need robots? Of course, there is a huge lack of there is a huge shortage of caregivers, right? But instead of giving you statistics that probably many talks give you, I'm going to just show you a glimpse of a life of some few months, the day of one person. This is a very cluttered slide, but let's read together. Okay? As a quadriplegic, my daily survival hinges on reliable and competent care providers. Yet in the last 6 months, I have cycled through 4 caregivers, each departure plunging me into crisis. This person can't afford a caregiver, but still this is happening. For example, after one provider left, I had no choice but to pay $300 for an accessible rental vehicle and transport myself to the ER. In nursing homes and hospitals, I often face additional risks, including neglect, the destruction of my adaptive devices, and the financial strain of losing most of my income to institutional care fees, leaving me unable to pay rent or utilities. Then a bunch of other things. The lack of continuity in care repeatedly uproots me from the only environment equipped to maintain my health and independence, which is their own home. A robotic helper designed to assist with critical tasks like catheterization, bowel care, feeding would provide an infallible safety net. Such technology would not only save me from the dangerous and costly spiral of emergency interventions, but also restore a sense of stability and autonomy in my life, preventing the preventable and ensuring my basic needs are always met, right? So this is where basically our labs and also labs here we are looking at physical robot caregiving. Now, as I said, it's contextual on the user, the environment, the caregiver, and who is giving the care. In this case, if it's a robot, robot's embodiment. Now, here is something that I want to really mention, right? As roboticists, we all want to build a robot that can do many different tasks. But when you deploy these robots in people's home for long term, nobody is going to use it if they don't feel like this robot is made for them. There is built to serve system serve many, but feel built for one. There is this always tension between generalization and personalization that you will see always come throughout my talk. Now, of course, this talk, physical robot caregiving is not something that we just started recently. It has a very rich history. Actually, with the help of one of the students, UW PhD students, Amal, we developed this history where basically the idea is around 1960s, one of the first manipulators, that was used, controlled using tongue switches, was used to pick and place. And then around 1970s, more wood spoon lifter came. This was used to lift spoons for feeding. Around close to 1980s, Meldog, one of the first robots to help people with visual impairments guide. These things came, right? So various robots for various applications. Later, some of these they became multi-purpose. Like this one, robot arm workable system, could do even some meal preparation. Handy one was used to feed, but also brush teeth and pick up things. This happened. Some of these applications got interest from people, and later on, bunch of companies came, especially in this feeding scenario. Many, at one point, like 16, 17 different companies existed in this feeding scenario. But very few exist now. And some of the reasons was that because in homes, when you deploy things in homes, there is so much variability that there was very little robot autonomy there. Also, some transferring system came like Riba. Now, because of that, so around this time, many academic research labs started working on adding intelligence to these robots, right? UW has this. This is where I did my postdoc. My lab falls in one of these. Fun fact, today, out of all those companies that are there, only Neaterator and OB actually remain commercially. And even though there also, people get it, use it for 5-6 months, stop using it after that. So my lab comes mostly around this. Mostly, this is how I tend to think of my lab. If I put this as a triangle, on the top are various applications. Robots feeding people, bathing people, dressing people, transferring people from bed to wheelchair. To support this, we work on various algorithmic directions. And to support this, we develop various tools, which I call is a toolbox, whether it's open hardware, simulator, software libraries, or data sets that people around the world or groups around the world are using. But even if you don't remember anything from my talk, the key message is this, that it's very important to be in constant loop with stakeholders, and here by stakeholders I mean occupational therapists, users for whom the technology is, caregivers, so that we are always grounded. The research that we are doing is grounded to real problems. Cool. So now let's dive a little bit into the technical aspects. So when I talk about physical robot caregiving, basically what we are trying to do is that, why it's physical? Because you cannot do these tasks without bringing the robots close to the humans. Not just close, like you have to physically touch. Without touching the humans, you cannot do these tasks. So this contact can happen from localized to whole arm to even whole body interactions. So let's first focus on localized contact, right? So for localized contact, I'm going to ground the work in this application of feeding, where contact happens mostly at the end effector with an utensil and the world, whether it's food or the mouth. So here you will see UW. Look at this. This is where it started. It was actually, this video was shot at the 4th floor of the other building, the Allen School kitchen. So here basically we are doing feeding, and so here basically the robot picks up a tool, and then using sensors it figures out what strategy to use using algorithms on the back end, and how much force to apply, and then going in front of a person to take a bite. We develop this we divide this into 2 parts: bite acquisition, which is the act of picking up the food, and then bite transfer, which is the act of transferring the food into somebody's mouth. Now, of course, this person does not have a visible mobility limitation that we know of, but later on I will show how we have developed on top of this and actually tested this with real people. So let's start looking at each of these phases, right? Let's look at bite acquisition first. Now, in bite acquisition, we have been able to pick up different meals. Some were directly store-bought, like bought from Wegmans, which is a local chain there, some were home-cooked, and also with a wide variety of user preferences. And we have deployed this across 2 sites and 3 robots. Basically, the way this works is, imagine the robot gets an image of this plate. Let's say this is a spaghetti on meatballs, meatballs on spaghetti dish. It gets passed to a visually conditioned language model that basically says 2 things: what food items are there and where it is on the plate. That gets passed to a structured task planner which outputs two things. Basically, the thing which outputs is how many actions do I need? Action here is not the next velocity or position. These are skills. So like skewering, pushing, twirling. Do I need to actually pick it up? So for example, if I were to pick up spaghetti, first I have to push the meatball and then twirl the spaghetti. If I have to just pick up the meatball, I just square it. Let's call this an efficiency score depending on how many skills I need. This goes to a downstream LLM that also takes the user's preference and then it uses chain of thought reasoning to figure out the action. So let's look at this. Here, let's say the person says, please don't feed me any meatballs. The robot tries to remove the meatballs. It failed. It tried to do it again, and it will keep doing it, and then it will twirl the noodles. Now, next time, realize that there is not enough not enough noodles together, so it's going to group them together, and then once it groups, then it picks it up. So did we solve it? No, still there are lots of failures. Failures happened a lot. Like for example, when you put rigid food items on soft things and other things, like many kinds of failures happened, mostly related to soft food items. And we tried various techniques. I'm not going to go into the depth of this. Like one explorer was, okay, maybe the issue is the action space, let's explore. But I cannot explore in the real world because the food will get destroyed. Let's do a real to sim to real approach to explore in simulation, figure out what converges, execute in the real. Okay. We tried multimodal skill affordance. Like during meat eating itself, even though the chicken nuggets look the same, some are harder than the others. So just visual information is not enough. Let's learn like visual and multimodal, visual and haptic skill affordances to figure out what strategies to use. And each of these helped. They helped a bit. But what we realized was, if our goal is to actually deploy this in people's homes, there is always some case where things are going to fail. Robot autonomy is going to fail, which means we need human in the loop. And here comes the main message here, where we wanted, like because of the long tail that can happen in people's homes, we wanted to use human in the loop. But when we use human in the loop, instead of just thinking from the robot's task performance perspective. Let's say you have an algorithm, your favorite algorithm, and it spits out a way to predict the uncertainty of an action. And when the uncertainty is high, let me query a user. Instead of just thinking about that, the main message of this is that let's also put human factors central to your algorithms. Because each query that you ask to this person with multiple sclerosis has an associated workload. So how do you trade off task performance and querying workload? Now to do that, it's a very simple idea. We developed this algorithm called query gap, linear CP query gap, where the idea is simple. Let's say these are various actions that the robot, again actions means like skills in this case, robot could take. And for a particular thing, what we take is like the best action and the second best action. So the lower bound of the best action and the upper bound of the second best action. We define that quantity as the pessimistic performance gap G. And if that's greater to this workload model that we prepared by collecting data from 100+ individuals, including individuals with mobility limitations, for different kinds of queries with failures that can happen for this task. Like with this, when you compare this, where if this is higher than query, then not. Very simple idea. Now, what does this lead to? So this is what happens. This person without a mobility limitation, if let's say the robot has an uncertainty, something it just can query the user, and the workload increases, but that's how it figures out how to pick up. But in this case, this person with multiple sclerosis, what you will see, if you look at the blue thing, like sometimes even if it fails, it will not query. But because it is always checking that trade-off, and then when it feels like it's to query, that's when it's going to query. And so basically what the behavior that results because of this is the following. Because of this, even if emptying the plate takes me 10 more minutes of time, that's okay because I am not putting too much workload on this user, and so this user has basically the resultant satisfaction goes higher. So the key message again here is considering human factors in these human in the loop approaches for user facing applications is important. This was just an action level feedback. We actually, go ahead.
In both of the previous examples, the meatball one and here,
Yeah.
I'm curious about the interface.
Great question.
Right? Here it seems like you're providing actions, there you're providing language, but for people with impairments, maybe you can't.
Yeah, so in this case, we had different interfaces. This person could speak legibly, so they were using voice to be able to talk. But for some other users, we are using, like people who are using SIP and PUF or something else, we prepared a web-based interface using which they could, basically whatever interface they are used to control the digital things in their life, that's what we're using.
And that factors into your query cost model?
Correct.
So it's like different for different people?
So yes, so basically we collected this data. When we created the workload model, we looked at what interface they were using, how many queries there were there, what queries were there, what answers they were giving, what was the frequency, all of these things go into the workload model. Okay. So we tried to extend this to more various kinds of, because failures can happen at everything. It can happen in object identification, it can happen in detection, it can happen in skill parameter selection, skill selection, even with some of the foundation models. But again, of course, things may change. This was still old, this has become old at this point. But it can happen. So, and we looked at various approaches. But the main idea was we were trying to look at which module, where is the failure coming from? Is it from perception, planning, control? What kinds of modules, if your system is organized as a module, which module should we query for? And then for this module, should you query or should you execute? We tried looking at various things, but again, the same thing emerged, which is for different users with mobile, and this was deployed actually in people's homes as well, that when we were actually deploying this, looking at both the user factor as well as their the task performance, the trade-off of that helps in increasing user satisfaction, at least from our limited user study. But this led us to think, what happens in 3 years or 2 years or even now? This foundation, every day, every week, something new is coming up. This robot, at some point of time, it's going to become so capable for this, this one task that these failures may not happen, let's say. In that case, what would the interaction look like? The person is sitting on a wheelchair. This robot will never query the user because there is no, it's just always confident of doing its task and it's going to just do like this. Is that the kind of interaction we want? This led us to another thing where we looked at, instead of being beyond, looking at workload aware, beyond workload aware, engagement aware interaction, where the goal is you ask the user before the interaction, what is the target level of engagement you want by doing some kind of calibration. And then the robot has a model that it uses to track this engagement over time. Now, if it happens that even if the skill confidence is very high, but the engagement according to the model, the engagement is not high enough, it's going to ask a query, even if it's a fake query. It does not use it for its downstream policy to involve the user in the process. So with all this, we felt like, okay, we have certain tools available to us ready to use when we deploy this in homes. But there's, yeah.
I really like the framing you have of so there's engagement and then there's effort, right? And if you look at that in the two-dimensional space, you want somebody presumably highly engaged but not putting in as much effort, right? And I'm wondering also whether, and I guess how does one think through that space, right? And I can imagine that individuals are different.
Yes.
And if you take this model, right, there is possibly a third dimension or some function of engagement and effort, where in your attempt at trying to engage someone, you may be asking them questions that make them lose trust in you.
Yeah.
Right. So there's I imagine it's really complicated, but I guess maybe you can take a step back and say what is the ideal interaction here? What does that look like? do you, yeah.
I mean, this is an open research question. We are still figuring it out. And I think as we deploy more and more, we'll know what it is. Right now, what we are thinking of is the queries that we are asking, it's related to the task that it's doing. While you are asking query, the workload, it never exceeds. The workload is, the way we have modeled this, that it never exceeds a workload like a threshold. Like workload is a hard constraint. And it tries to manage that engagement within the desired engagement level as much as possible. Now, of course, if as you said, like for example, the reason this engagement, like how do we know this desired engagement? We ask the user before every interaction. So it may happen that in their first day, they want to be very engaged because, or they don't want to they don't trust the robot. So it's very high, but as they use it more and more, maybe they are engaged, or maybe it's at a different time of the day or something else, their engagement level, design engagement level is low. So that is a user knob. That user will tell what it is, and that's how this algorithm works.
And then how are you measuring engagement?
Oh yeah, so this is basically a calibration. We ask them various questions, and then we ask, if we were to ask this question 3 more times in this amount of time, will you think this is annoying versus, or is this something that you want? Would you want to have control over this? Like that's how we are calibrating this.
I see. So I guess like here a failure point might be that like I might be super engaged. Like I'm listening to your talk.
Yeah.
Right? Like I'm incredibly engaged. Yeah. But like you don't have to ask me questions
Yes.
to maintain my engagement.
Yes.
I guess like, but in the lack of any other observability,
yes.
then this is a viable, like
yeah.
you can ask
That's
me,
a good point. That's a good point. Yes.
Like I guess it's a little bit like you're teaching me. And like oftentimes as teachers, we like poke a question at the audience
yes.
just to check their engagement.
Just to check their engagement, yeah, that's how we're doing this. But I mean, there are other things. So one of the things, you can also look at various other multimodal approaches. Like you can figure out their engagement instead of being so implicitly through eye gaze, through other things. Can you infer the engagement?
Like I'm gonna say a word that I don't know very well. So like valence, like there's all these terms and like.
Okay, so I'll tell you. Yeah. I think there are so many things that we have been thinking about. First we thought, okay, is this agency? Is this, what is this? And so we were like, no, we don't know this enough. Right. So we wanted to really understand what this is before saying this, but this was, this felt safe to say, so that's what we used. But I think this is definitely related to agency, but I think agency is more than this. Yes. Yes.
Yeah. Is there a model though with the human caregiver for engagement, workload, like?
So that's what we created. Like we couldn't find even any data sets or any models there, quantitative models. There are theoretical models, but so that's where we collected data over with hundreds of individuals for this scenario to get that model. Yeah. Cool. So this was just the first thing, which is like picking up. What about transfer? And this is such a challenging problem. Like once you pick up the food, how do you transfer into somebody's mouth? And the reason this is challenging is this. The physical interactions are very subtle. Imagine, like this person with spinal muscular atrophy has very narrow mouth opening, like this. You have to feed, put the entire food and the fork through this. There is no contact-free trajectory. This person with schizencephaly has very poor jaw control, weak bites. Person with arthrogryposis has very specific, they can only chew food from one end of mouth. Sometimes when caregiver doesn't know and if they cannot speak legibly, they use their tongue to guide the fork to do this. Person with multiple sclerosis has spasms. Imagine a robot. I mean, you all work with robots. Robots coming with a fork and then suddenly there is a spasm. Like what is the safety implication is huge. So the way we tackle this is basically 2 things. There are many things there, and I'm going to go into the detail later, but on a high level, very accurate and fast mouth perception that works even under occlusions. Because we saw this even here when we started. When you bring you have to really know the state of the mouth even like milliseconds before you feed. And the fork itself, the food itself is occluding the camera, even if the camera is here. And of course, you have to have very physical interaction aware control. So just to give you an example, this physical interaction aware control, right? imagine what the robot has to do. So like the way we are doing this is, of course, we are using multimodal sensing, visual haptics. We have a physical interaction classifier that triggers different downstream controllers. And so now, let's say a robot doesn't know where to feed you. The robot first feeds you at the center. Now the person, like a person with multiple sclerosis suddenly has a spasm, which means the robot has to be very compliant, right? Like if it's rigid, it can literally like poke somebody. It has to be compliant, but it also has to understand that this is unintended contact. So it doesn't need to learn from this. But at the same time, the person who is using their tongue to move the robot, that person, like for that, the robot needs to know this is intended contact and learn from this interaction so that next time the robot actually feeds them there. And so that kind of subtle interaction is very important. I'm not even going to go into the safety part. I'm going to the later about how we dealt with safety. But that's basically the key insight. So using this, we are able to actually feed people with all of these arthrogryposis, different levels of spinal cord injury, multiple sclerosis in a hospital, in somebody's home, as well as in our lab. There's one particular interaction that I always show in my talk because it gives us a lot of like I would say like a very like just the emotions expressed shows us gives us the impetus to keep working on this problem. This is a father. Mother is in the background.
I like it too. It's my favorite burger. You like strawberry?
Mother started crying. She had actually lifted her hands like this, like arms like this. Again, this robot is far from, it has still not reached the maturity to deploy this long term yet. We are working on this now, deployment. But even these things keep us grounded and keep us pushing.
It's my favorite burger. You like
Now
strawberry?
feeding is not just dietic, right? It can also be social. So we have started looking into like social dining, and there is a fantastic work actually from UW also on this. But here the main idea was we are looking at bite timing. The whole point was how do you predict when to bring the food near a person's mouth without disrupting the social conversations? And we are trying to predict if for people who always eat together, like friends who eat together, can I predict just by looking at the other co-diners, can I predict when you are going to eat? Okay, so now let's come to the real home deployment, right? Because that's where the real excitement is. So again, when we did real home deployment, still this is short. We have done this only 5 day, a 5-day deployment. But what changed? This took us 2 years to do this. What changed? 3 things. First, huge variety of user requests. We did so basically, when we reached out to people, like we did a formative study, like what matters for you for feeding? Even just for this one task, and like we had a limited, I think around maybe around 20 users with mobility limitations that we chatted with. We got 46 different personalization requests with that sample. Imagine doing this for hundreds and thousands of users or even millions of users, right? Huge variety of user requests, which basically means it's just like impossible to train everything like in your lab. You have to do this like adapt in real time. On the fly personalization is important. Second, observations are very important. We just kept observing how fed in this home. That helped us identify various edge cases. And in some of these cases, even though some of the rhythms we had developed, many of the assumptions started breaking. So there, what we did to be able to do this, what is important is formative studies, but also safety, not just at the algorithmic level, systems level, layered safety in each aspect. And finally, there are many unknown unknowns, and I'll give you examples of this, that we did not observe. And when we deployed this, it happened for the first time. Thankfully, we had predicted that this may happen. So the last line of defense has to be hardware level safety, that the hardware itself is incapable of hurting. Because again, this is a very intimate interaction, right? Like a fork coming inside your mouth. Imagine like the IRB, like what can happen. So again, the main thing here to look at is first.
Because like one point I would also say is that like although this seems like unsurmountable, And like, you can draw all these analogies to driving and other things where like, you're working in the home. I guess like one big difference, like you pointed out in your video, is the fact that like you have these people who are your users are deeply invested in the success of the system, right? Like, so there is some co-adaptation that happens, which gives us hope that like we can solve this, right? Like I understand.
Yes. Co-adaptation will happen with every like users will adapt. So right now we are only looking at one side. I think this will show up when we do very long-term deployments. Users will adapt. Absolutely agreed with you.
But it's also, it's a beautiful application to look at because like your early adopters actually want this, right?
Yeah.
Like they care about it and they want it instead of like putting something somewhere which is going to take their job.
Yep. Yeah, that's true. Cool. Okay. So what are the key things here instead of looking at all these details? First, need for flexible interfaces. Because every user can, when they communicate in different ways. So we had given them different interfaces and including gestures that they could design on the fly, like basically through a calibration setup on the fly when we deploy it. Then, of course, a bunch of different skills that were composed together, where each skill was a behavior tree, and then there is this safety. Let's jump into this safety a little bit, right? So the way we did this, and this system, we are only able to do out of those 46, only 36 out of those 46 personalization requests. Two things happened. Like so for the safety, basically this safety watchdog, which is personalized to every user, is what basically helped. Like so, what happened was, we had obviously the usual safety that people use, like bounding boxes, tracking people's head. Force shock sensor or if that violates, force shouldn't violate, compliant control, active collision monitoring, things like that were there. This is where the known unknowns went, like where we had like it had like around 50, 60 rules. It had to pass through all of these rules for us to be able to deploy. Any command will only be executed if it passes through all of these. And then finally, the tool was designed in such a way that even if it passes through this is the unknown. Like it will, like after a certain amount of force, which we measured, safe, the fork is going to break, the wheel strength is going to break but not fall on the user, it's going to fold. So that's where we are able to do, and so here is an example, right? So here you see initially, so this person is using, do you see this? This is their web interface. They're using the web interface to first calibrate the system, how they want the system to behave. This thing that you think is moving is a nose tracker. It's a tracker that's mounted on the nose, and they're using this to do that. Now, as they do this, the robot then the behavior is personalized, and then it's going to see. You see, the robot is going to feed them, as well as drink, and then wipe their mouth. There were two interventions that happened during this 5-day deployment. One was the food had to be heated, so my student heated the food. And the second was one time this user interface hung, so they had to reboot the user interface. You will see actually Rajat or my students show up in, to fix this. Another thing that is very important is that for an end user who is not technologically savvy, to be able to personalize according to their behavior, transparency is very important on the system side. They should be able to know what the robot is doing or thinking. In this case, we did this in a simple way where basically the person would ask, like let's say they say, oh, wait for 5 minutes or wait for 3 minutes for doing something, and it was because it was using LLMs, it hallucinated, and it started waiting in multiple places. Then it's like, this is not the behavior I wanted, why are you waiting more? And so the robot was able to use his thinking test and others to be able to tell what it did. And that led to a kind of an interaction between them, that he gave basically a command or a behavior that was more specific, that the robot was able to do what they wanted it to do. So the point again is that whatever mechanism we use to personalize, in this case we are using foundation models, it's important for the user who is not tech savvy to also understand what the robot is doing, and that capability is important. That's basically the key insight. Yes?
So, here you're using like spoken whatever instructions, or like the user is saying
At the beginning, he said,
okay.
But during, he didn't, because like this, so these users, if you look at their lives, right, even if they can speak, after some time they may become tired. So for many other detailed or these things, they may use some other interface to do it.
Of mouth wiping, but
If you're using foundation models as your adaptation tool, you're typically going through text and like context or something, right? But like so much of personalization might be implicit or tacit or like hard to verbalize.
Yes.
And like how do you do that?
Very good. Let's go to the next point. Yes, very great question. Great question. Right now, in this case, everything is explicit. If the user does not explicitly say it, the robot is not going to be able to personalize. But you made a very good point. So for that, so basically, and another thing that you saw here was personalization. It was about different things, behaviors, but let's dive a little bit into the physical robot caregiving aspect, which is the contact preferences. Like how do you personalize to contact preferences, right? So to do this, basically I'm going to ground this to another application, let's say bed bathing. Here a robot is actually bed bathing a person with multiple sclerosis, like pronated arm. So here one of the policies that we are using like at the end, like to be able to deploy this is, many people still get diffusion policies, right? We're using this. Now, how can you, during inference time, how do you, for a downstream chain, how do you actually cater to users' preferences, both implicit and explicit during inference time? And so we basically propose this RAG-def idea, where the idea is this. Let's imagine that it's a transformer-based, diffusion policy. Now, their preferences can be explicit, the user actually mentions it, or implicit. And so the idea here is that for a new situation that happens, we maintain something called a memory pool. So whenever you get an observation, it passes through an encoder, in this case it's a VLM encoder, that projects it to a space, and we look at, has this situation happened before? And if this situation has happened before, we take the observation and action embedding, put it as an additional cross attention layer to do the, basically to get the policy for this. For explicit ones, whether it's interaction, how much force to apply, avoid certain area, spatial constraint, semantic constraint, whatever, we just use usual value guidance to be able to do this. So here, for example, using this, we are able to do this bed bathing. Now again, this is not as mature as our feeding line of work. We have not only tested this with, we have not tested this in homes to be able to do this. But using this, we are able to cater to users' preferences, implicit and explicit. But again, there are a lot of assumptions there in terms of how much it will scale, and lots of questions about the embedding itself and things like that.
How should I interpret the these 9 videos?
Sorry. Basically, these are just different trials with different preferences. The green means success, in red means where it failed.
I see. And these were preferences that were collected. How were they?
The user was this is a mannequin, but there was a user present, and they gave different preferences, and we checked each of these preferences on the fly.
And then is there, can you give us an idea of just the qualitative differences that we should be looking out for between this?
I see. So basically,
they all seem to be very successful. So that's what I'm trying to figure out.
So for example, there were 2 things. One was there was an area that they had to avoid, and the other one was the force, which you cannot just see from this, but it was whether the force exceeded the threshold or something like that.
Got it.
Okay. In the interest of time, let me quickly move to a couple of other things that I want to mention about. As I mentioned, that physical robot caregiving is not just, and the contact scales change, right, from localized to whole arm to whole body. So let's quickly look at a little bit of whole arm and then whole body. And again, for each of these, both the hardware and software need to evolve. So here was an example. Again, this was done purely with a mannequin. We have not reached the maturity to do, this is what we are working on now. So this robot arm has a whole arm skin sensor. It's a Wi-Fi based skin sensor that we have used, and it uses this to use like basically to do tasks that are relevant for bed bathing and transferring and things like that, such as rolling over, like a mannequin and things like that.
That's the commercial sensor?
No, we made it. So each of these are FSRs. We stack them together. Do you this gray thing that we see? Underneath are basically the sensory boards, and so you don't see any wires. So our original sensors that had wires, whenever we started doing whole arm manipulation, it breaks. It was not stable, so we did this completely Wi-Fi based. Yes?
You mentioned FSRs. What are FSRs?
Oh, sorry, force sensitive resistors. These are probably the most robust tactile in the sense they are not very high resolution, but they are very robust. Like you can literally press on them and they will not break. You lose accuracy, you lose resolution, spatial resolution and temporal resolution. But the things that it had, it was enough for these kinds of broad tasks. Or even doing limb manipulation, like lifting, things like that. And the key idea, again, I won't be able to go too deep into this, but the key idea was three things, again, like in terms of this, right? One is context-centric representation. Once you have the representation, sampling, contact-aware action sampling, and then a predictive model that is hybrid predictive model. So for representation, basically we used all kinds like RGB, depth, as well as proprioception, and as well as tactile readings from the sensor. Again, note, from RGB and depth, we are not really looking at RGB. We are basically just using this to get the distance field and the contact map. That's how we are doing this. We are not looking at the actual RGB scene. Then for sampling also, basically we do the sampling in a way that which directions we should sample the action that has the maximum effect on changing the force, contact forces. So basically normal to the contact force, like either going up or going down, right? I'm not going to go to the details of this. And finally, when we predict the model, looking at both the not only the latent model, latent prediction, but also kinematic prediction. That's very useful. If basically we tried to use the best of both worlds, where this latent model rollouts helped us to predict when a contact may happen, may break, and things like that. But this gave us structure, like using just kinematics gave us structure, and we use this hybrid rollout scoring to get the best rollout. And turns out this hybrid rollouts actually helps even in other world models, whether you use Dino world model or even like VJPA2 or something like that. Adding the structure helps. So once we had this, again comes the question of a personalization. How do you personalize to contact preferences? So this is where the idea was that tactic generates this reference trajectory, and then priority touch personalizes this. It removes this. So how does this work? Here also we explore different actions. Like suddenly, let's say the robot is going around and pulling me or rolling over, and suddenly somebody says, oh, I don't want to be touched this way, or like apply less force somewhere. You have to explore different actions. But here, an action is a hierarchy of controllers itself. That is the action. So the topmost one is the highest priority here. This controller, CP, let's say imagine there are various controllers at different contact patches. This only works at the null space of this controller. This only works at the null space of both of these controllers. That's how we maintain in the hierarchy. And for different action, we change the hierarchy to see which one works. So using this, we started with a prior. This was done in collaboration with TRI, where do people generally like to be touched, how much forces they have. We start this with a prior, and now this is what happens. Let's say this robot is bathing that arm. Again, this is a skin. And once that happens, it comes in contact through the whole arm, like here you see a human. When that happens, let's say the person says, please apply less force on my abdomen. It's very dangerous to explore here. So it goes back to a safe configuration. It starts a digital twin. It doesn't have to be visually realistic at all, because all we are doing is a contact based. So we start with because what matters is the speed here. So we did that. Then we run an algorithm where basically it's just each action is a ranking of the controllers. Which ranking can lead us there? Once it converges, we do this in the real world. And turns out this actually works. Like this again goes beyond just physical human robot interaction to even this cluttered manipulation, where the robot can snake around different objects and then like go to a certain point. With this one we did like human subject studies, and people seem to prefer this. Finally, I want to go to whole body, and this is where I want to like again I will not go deep, but I want to say that every hospital I chatted with, every rehabilitation department I chatted with, the first thing that they told me was to help with transferring people from bed to wheelchair and things like that. And this is where you need whole body interaction, but think about the robots that are there in our like that I was using, or that are safe to deploy, let's say in homes. They are torque limited. Kinova arm doesn't have the payload to lift a person. So to do that, we decided, okay, how do people, occupational therapy caregivers do this? They also have the same issue, so they use assistive devices that are already present in homes. So we first developed this kit called Flex ADT that can convert top 3 like the wheelchairs that are available, Hoyer lifts that actually lift patients. If you don't know that, if you mostly see humanoid robots are being lifted, they are also lifted using Hoyer lifts. Those are the lifts. It converts these Hoyer lifts, wheelchairs and hospital beds into instrumented agents. This is a kit that sends out, that we can send out to do this. Now, once we have that, what we do is the robot arm mounted on the wheelchair does this like dexterous tasks like tying the sling's hook. But the Hoyer and all of this work together. So let's see when the wheelchair goes on that side, Hoyer sling is far, it goes closer, and then the robot will pick up the deformable this sling hook, and this will work together. Think of this as a deformable peg in hole kind of a thing. They are working together for it to tie. So it goes around, it ties all of this sling hooks to each of those hooks. Once that's done, then the Hoyer lift will lift this mannequin. Then the Hoyer lift and the wheelchair will work together to gently place. This system again, it has lifted me and my students, but we have not done user studies with IRB is still pending. There's a lot of stuff we have to do to get there. Okay, so and then it does this, right? Okay. In the interest of time, there are various other physical caregiving projects that we have done, like data sets with occupational therapists, multimodal data sets, different meal preparation things, representation learning of human functionality. If I know what the human is capable of doing, I can provide just right assistance, not over assistance, not under assistance, things like that. One quick plug, we have been doing this competition. We just did it one time in ICRA 2025. This is a simulator that we have developed. 56 teams from 17 countries participated using this simulation round, and then top teams, 5 teams were selected for 2 tracks, dressing and bathing track, when they came to ICRA 2025 to do this with real mannequins and real arms. Not all teams could make it. 3 teams could make it because of visa issues for this, and 1 team for this, and the winners got each prize. We are hoping to do this again in ICRA 2027 in Korea. So please participate. Cool. So now to conclude, what are the key insights that we have learned? Or let's call this a recipe. Again, when I say recipe, I am not saying I have a solution. This is what you have learned so far, and this is constantly changing, and it will probably change. But one thing is, what you have learned is, even though we use the power of foundation models, and that has helped us a lot, it's very important to have context-centric and user capability-aware representations that robot policies can use. We still are not going complete end-to-end for these physical systems. We have learned skill. The skills can be learned and all of these things, but we are composing them together when we deploy this in people's homes. Of course, we use for exploration, we use simulations as much as possible. But here is a thing that I want. When we use human in the loop, let's not use humans just as tools for robot performance. Human factors should be central. Stakeholder integration from the beginning is very useful, and even studies outside the population can be very informative. So that's important. The step for personalization, the way we are doing this so far is that we have an out-of-the-box generalized system, but then we try to calibrate it as when we first introduce it to the user, and then for the residuals, the users always do on-the-fly personalization. But for that, you need flexible interfaces. It's extremely important, and you need transparency in the system. And finally, I am a strong proponent of modular hardware and software to cater to user preferences. I cannot tell you how many times this has helped us. I'll just give you one example in the interest of time. One time, when we deployed this in a hospital, in a user, we put the food, a plate, and we wanted, like, the robot was ready to feed the user. User just said, I am not going to eat with this robot. No, it's like, okay, the occupational therapist, when we deploy, we always have an occupational therapist, the caregivers, what's going on? Turns out, this person just does not want to eat when the fork is like this. They want the fork to be inverted. It has to be like this, otherwise they are not going to take a bite. Because our system was modular enough that we could immediately just turn the fork back, and it was able to do this immediately. So that really helped. This person was, like, when you place the food has to be, the plate has to be placed in a certain place, otherwise the person refused to eat. The point is, with many physical limitations, there are also derivative cognitive things that can happen. And so there are things that it's very difficult to train for before. When we go across deployments, give me 1 second and then you can ask me. I will come to you first, I promise. One thing that helped us to go from one robot to another robot, even their workspace was different, was extra degree of freedom on the tools itself. That helped us easily to go from Quinoa to Franca to WidowX arms and things like that, because this compensated for those differences. And finally, the safety guardrails are extremely important, but they themselves have to be personalized to a user. Well, this is my general vision, because what we recently published this thing called a care eval, where we looked at state-of-the-art LLMs at that time when we published, like around 10 or 12 different open source and proprietary ones when we tried this. And we asked not even action level, like physical things. Like, we just asked, like, let's say you have a user with, let's say, wants to, I have this condition, I can move this, I cannot move this. Can you tell me how to assist somebody with dressing this shirt or feeding this, or just pick them up? And the things that occupational therapists care about, we actually created a benchmark with occupational therapists, a bunch of question answer, like questionnaire benchmark. LLMs are not that good. They were not that good. So there is a lot of work to do in both generalization as well as personalization. But my hope is we can reach there a certain point where we have this pipeline of high-level contextual reasoning, where it's contextual to user, environment, tasks, and the robot, and the caregiver, and self-case-based acquisition. We have started developing these tools, whether it's real data sets, simulation platforms, or other frameworks to be able to achieve this, but there is a lot to do. But the goal is to augment caregiving when caregivers are available, not to replace them, but when it's not, help them. It's very multifaceted and contextual, as I said. This is our lab, and yeah, thank you so much. Yes, your question. Yes.
The example you gave for the benefits of having a modular software or hardware system was converting the fork, but I guess there's multiple layers to it, right? Like, if you were skewering a meatball, it's probably, you can like hard code it in the software to just say that just keep the fork inverted. But if there was like some other kind of food, it might lead to like the food itself falling.
I agree. So my point is, when we were deploying this, we didn't have time to code. Literally, the system should have flexibility that when the user requested, we just switched it, and at least for the, I cannot claim that it would work for every food item that there is, but at least the food plate that the user wanted to eat at that time, it worked. That's the point. Like, so build as much flexibility as possible in that in the system. Imagine if I were to do this, a policy which was just looking at you know, I don't know, where the fork is mounted or like the tips with based on that with the image, this will become a little bit tricky, right? That was the issue. Yes.
I have a question. So I think like one of the biggest problems people see with like generalized humanoids is you're not, when you give an instruction, you don't really know what exactly the robot is going to do. So in this case, are you visualizing some of this trajectory, especially in, like, or is the
Very
user
good
just
question.
trust enough to?
Very good question.
Yeah.
So basically, it's this. So we followed this thing called an IEEE standard for transparency. So here, take a look at this. This. It had all, depending on the, it had all these levels. Level 1 is just accessible information. We can provide a manual to the user. If the user wants, they can know what the robot is doing. Level 2 is interactive simulation. So let's say they ask something. Well, how would the robot behave? How would the trajectory change? That has to be there. Level 3 is user initiated explanation. Level 4 is hypothetical. User may ask, what if I did this? How would the robot react? These scenarios. And level 5 is continuous explanations, even if the user is not asking. The system had capabilities for each of these 5. It depends on the user what they wanted. Very good question. Yeah.
I think we're at time, unfortunately, so we'll have to like defer questions for later. But let's thank Tapo again.